Swayam Prabha. Digital India. Educated India.
Hello students, welcome back to the discussion on phase equilibrium, where we are applying the principles developed for thermodynamics of open systems, and we have already seen that our current topic of discussion is the effect of variation of both temperature and pressure on two coexisting phases of a pure substance in equilibrium. Now, we have seen that if we examine the phase diagram of real substances like carbon dioxide or water, we find that here the phase coexistence is quantified in terms of a phase boundary, which appears as a curved line or a nearly linear behavior in the pressure temperature phase diagram. And when we looked into the phase diagram of water, we found that for the solid liquid coexistence line, that is this phase boundary, it was very steep, and there were regions where I could see that there is a change in the shape of the phase boundary. Then came the question of how do I correlate the location and shape of phase boundary with respect to some measurable property of the system. And in this connection, we derived the Clapeyron equation, which is given by dp dt, that is equal to delta S transition by delta V transition. So the situation that we have in mind is we are located on the phase boundary between the two phases alpha and beta, and I am asking the question, if these two phases still coexist in equilibrium at a given temperature T plus dt and P plus dP, if I change the temperature from T and pressure from P, what would be the relationship between dt, dP and the thermodynamic changes associated with this change in temperature and pressure? And therefore, exploiting the fact that at both the states A and B, I must be having the equality of chemical potential of each of the phases of the given substance, we could derive what is known as the Clapeyron equation. Now, you must realize that this equation applies to any phase equilibrium if I am dealing with a pure substance. Now, what we are going to do next is I am going to apply this relationship and look at the specific case of solid to liquid phase boundary. So this is a typical zoomed in version of the phase boundary between a solid and a liquid. And here I have chosen to work with 2 points, where the first point is where the temperature is equal to T1 and the pressure is equal to P1. And this is the second point where I find that the temperature is equal to T2 and the pressure is equal to P2. As you see, since both the points are located on the phase boundary, therefore in both the cases the solid and the liquid will coexist in equilibrium. And therefore, if T1 is the melting point at P1 and T2 is the melting point at P2, then I can apply the Clapeyron equation and write that dP dt for this coexisting solid and the liquid phases of a pure substance that must be related to delta S for this transition divided by delta V for this solid to liquid transition. And we know that when I have a transition between a solid to the liquid phase, then delta S transition is nothing but delta H fusion by the temperature of the fusion. And therefore, I'm going to replace it by delta H fusion divided by T. So now this is my starting point for the analysis, that I have dP dt that is equal to delta H fusion by delta V fusion into 1 by T. Now what I can do is, I can now carry out an integration, provided I can write down this equation as delta H fusion by delta V fusion into dt by T. Now carrying out the integration is going to be simple if delta H fusion and delta V fusion are independent of temperature when I am going from this initial point T1 to the final point T2. So in this case, I will do this integration and temperature will vary from T1 to T2 and pressure accordingly will vary from P1 to P2. And therefore, I can write P2 minus P1, that is equal to delta H fusion divided by delta V fusion into ln T2 by T1. And here, this is the result that we have obtained by the application extension of the Clapeyron equation to the solid to liquid phase boundary, when I am changing the melting point at T1 from T1 at the pressure P1 to T2 at the pressure P2. Now you would notice here that when T1 and T2 are very close to each other, the melting point varies nearly linearly with pressure. But here what we have done is, we see that delta P, that is P2 minus P1, is dependent on a logarithmic function of T2 by T1. So this tells us that if T2 is approximately equal to T1, I can carry out a simplification. And what is this simplification? I can write down in that case that delta P would be equal to delta H fusion by delta V fusion into ln of 1 plus delta T by T1. Here I am using as delta T the small quantity T2 minus T1. If that is so, then what can I do for delta T nearly equal to 0? I can say that this quantity is now going to be approximately equal to ln delta ln 1 plus delta T by T1 would be approximately equal to delta T by T1. So in this case, what we can do is, now I can write down delta P as delta H fusion by delta V fusion into delta T by T1. And therefore, I find that delta P is going to depend linearly on delta T, and therefore if I change the temperature, I am going to see a linear variation in the value of the melting point as the pressure changes from P1 to P2. And this brings me to a summary of what I have worked out in this slide. So all I'm trying to show you here that the application of the Clapeyron equation to the solid to liquid phase boundary gives you an exact representation like this. But if you have T2 very similar to T1 such that T2 minus T1, which is delta T, is very small quantity, you can rewrite the equation shown here as this, and that tells you that the melting point would vary linearly with pressure. In the next example, let us examine the liquid to vapor phase boundary. Here, once again, we are looking at 2 points here. So what is this point? This point corresponds to the boiling point of the liquid at a given pressure, and this point corresponds to the boiling point of the liquid at a higher pressure. And as you can see that here the shape of the phase boundary is not linear. Rather, it is a increasing curve, very much looking like an exponentially increasing curve. Now let me see if I can quantitatively justify as to why this liquid gas coexistence curve would look like this. Once again, I will start from the Clapeyron equation. And now I understand that I can replace delta S for the transition by delta H vaporization by T. So what is delta H vaporization? That is the enthalpy of vaporization as the system goes from the liquid phase to the gas phase at a temperature T. And what is delta V transition? That would be the change in volume as the system moves from the liquid phase to the vapor phase. Okay, if that is so, then what we can do is as follows. I can say that delta V vaporization by definition is molar volume of the gas minus molar volume of the liquid. Now you know that the molar volume of the gas is much greater than the molar volume of the liquid, and therefore I can approximate this difference by the molar volume of the gas itself, and I can neglect the molar volume of the liquid. And if I assume ideal behavior for the gas phase, then the molar volume can be easily written down as RT by P. So when we do this, the result that we can easily write down for the liquid to vapor phase coexistence at the phase boundary as dP dt, that is equal to delta H vaporization divided by T into RT by P. So what is this quantity? This is nothing but delta H vaporization by R into P by T square. Now I understand that it should be possible for me to carry out this integration, but before that I need to do an algebraic reorganization. So what I will say is this equation then gives me dP by P, that is equal to delta H vaporization by R into dt by T square. Now as you see that I now have a relationship between pressure, temperature in terms of their differentials dP and dt, and here the situation I'm looking at is if the liquid and the gas phase was at equilibrium at pressure P and temperature T, and if I change the pressure by an amount dP and correspondingly the vaporization, the boiling temperature changes by an amount dt, then dP and dt are related to each other by this equation. But now if I am interested in a finite change in temperature and a finite change in pressure, what I will do is I will carry out this integration from a temperature T1 to T2 and go over here do the integration from P1 to P2. And therefore, what I am going to get is ln P2 by P1, that is equal to delta H vaporization by R with a negative sign that comes from this integration, and then 1 by T2 minus 1 by T1. So as you can see that this expression tells me that if I change the equilibrium pressure from P1 to P2, there will be a corresponding change in the temperature of equilibration, that is the boiling temperature of the liquid from T1 to T2. And the change will be depending on the delta H vaporization, which in this case is assumed to be a constant over the temperature range that we are working with. Now let me put this whatever is there in the right hand side as minus xi. So what is xi? The quantity that I have written down here, this is xi. Therefore, I can write that ln P2 by P1 is equal to minus xi. Therefore, I find that P2 is equal to P1 into e to the power of minus xi. If that is so, then I do expect that P2 will increase with pressure. Okay, so what I expect is P2 is going to have an exponential dependence on temperature. Okay, so if I go back and write this down, then what I have got is as follows. I have shown you how to do this derivation under the approximation that the gas phase is behaving ideally, and I arrived at this expression where dlnp dt is equal to delta H vaporization by RT square, and then I integrated it and showed you that this is the relationship between P2P1 and T2T1, and I also showed you that P2 is bearing an exponential relationship to P1. Now, if I move further ahead and look at the solid to vapor phase boundary, once again I understand that this is going to be a nearly linear behavior or an increasing behavior with increasing pressure, increasing temperature of equilibration, that is a temperature of sublimation with increasing pressure. So once again in this case, I understand that the delta V of sublimation can be replaced by molar volume of the gas minus molar volume of the solid, and since the molar volume of the solid is much less than the molar volume of the gas at a given temperature and pressure, I can neglect this quantity and equate the molar volume of the gas to RT by P for the ideal gas. So once again, I am going to have dP dt that is equal to delta H sublimation into P by RT square, and therefore I can write dP by P that is equal to delta H sublimation by RT square into dt, or else I can write d ln p dt, that is equal to delta H sublimation by RT square. So, this is the differential form of Clausius-Clapeyron equation applied to the solid to vapor phase boundary, where we have assumed ideal gas behavior for the vapor phase. And now I can do the integration and obtain the integrated form, and which is given over here. So, once again we find that this is the differential form for the Clausius-Clapeyron equation. This is the integrated form of the Clausius-Clapeyron equation, and it says that P2 has a dependence, exponential dependence on the equilibrium temperature between the solid and the vapor phase, which tells me how the change in pressure is going to affect the temperature at which the solid and the vapor phase would be in equilibrium. So, to summarize this portion, we say that we have studied the location and the shape of phase boundary in terms of one component or a pure substance. We wrote down the Clapeyron equation, whereby we found that dp dt is equal to delta S transition by delta V transition. Then we looked at the solid to liquid phase boundary, and when we applied the Clapeyron equation to this situation and integrated the resultant differential equation, what we find is that for a change delta P of the equilibrium pressure, there will be a change delta T in the melting point, which is given in terms of measurable quantities for this transition, namely delta V fusion and delta H fusion. Now, when we look at the liquid to vapor phase boundary, we found that we can actually rewrite the Clapeyron equation and arrive at the Clausius-Clapeyron equation. But here, to do so, we have assumed that the volume of the gas phase or the vapor phase is much greater than the corresponding condensed phase. And here what I found is that in that case, this is the form of Clausius-Clapeyron equation, which tells me that d ln p dt, that is given by delta H vaporization, that is the enthalpy of vaporization, divided by RT square. And also we could show that for the solid to vapor, the delta H sublimation plays a crucial role in the Clausius-Clapeyron equation, and we can say that this delta H sublimation can be compared to delta H fusion and delta H vaporization as shown here. Now, with this application, basic ideas in mind, let us now go to a simple application. Let us say that we are trying to design an ice skating shoe. Now, please remember the principle of ice skating. If I am trying to walk on ice, in that case, I require these special ice skating shoes, because otherwise we'll slip, and obviously we won't be able to do anything like the acrobatics of ice skating that the athlete is showing here. So, the crucial part here is the pressure which is going to be exerted by the shoes on the ice surface. Now, under the given pressure, I would like to decrease the melting point of ice right below the shoes. For higher pressure exerted by the blade of the ice skating shoe, I am going to have a lowering of the greater lowering of the melting point, and therefore I will have at the normal atmospheric pressure water in the liquid phase under these blades. So that is the principle. Now let us go ahead and try to do something like the design of the blade that ensures the contact of the shoe on the ice surface. And while doing that, we are going to use the following information that we see here. We know that ice melts at 273 Kelvin at 1 bar, and we also know that delta H fusion in this case is a quantity that is known in the literature, and you can find out the delta V fusion also from experiment. With this, let me say that I design a blade that is 30 centimeter long and 3 into 10 to the power minus 2 centimeter wide. Now, is this a viable design of the blade? So, then the question would be, what is the pressure exerted by each blade on ice if a 50 kg skater is going to wear it? Now, as you see that since there will be two such shoes, therefore the 50 kgs very approximately will be divided into on each shoe, and therefore I have to think of the weight on each blade to be half of 50 kg approximately. Now, what is the area of each blade in contact with ice? That would be given by the length of the blade and how wide it is. So, I can very easily show that the area of each blade in contact with ice is going to be this much. Then, if I assume that the weight on each leg is about 25 kg, in that case, the pressure on each blade is 25 kg, that is the mass. Then I multiply it with g, that is 9.8 meter per second square, and I divide it by the area over which this weight is acting, and the answer we find is it is 27.2 into 10 to the power 5 joules per cubic meter. Now, as you see that if in order to understand the viability of a design like this, we next have to understand under this pressure what is going to be the melting point of ice. Then I find that this I can very easily calculate by using the integrated form of Clapeyron equation. And here I see that delta T, using the values of delta V fusion and delta H fusion from the literature, delta T is obtained as minus 1.92 Kelvin. Or in other words, when a skater is skating, the melting point of ice right below the blades is roughly about minus 2 degree centigrade. Now, we have already seen that then if I think about the ice at 273 Kelvin, ice will no longer exist at this temperature as solid, rather it would melt and the liquid water is going to be more stable phase, and therefore the design that I have shown you here, this is going to be a right kind of design, so that you will have a thin layer of water providing you sufficient lubrication such that we can very easily use these ice skating shoes with this kind of dimension of the blade to perform the acrobatics that we have seen in the previous slide. I would like to conclude the lecture today by saying this. We have taken very simple applications of the concept that when two phases of a given substance are in equilibrium, I understand that the chemical potential of that substance is the same all throughout the sample, irrespective of the fact that now it does not exist in one phase, but it exists in two phases. So what would have happened if I had three phases in equilibrium, just like the triple point in the phase diagrams that I have talked about? In that case, once again, if alpha, beta and gamma are the chemical potentials of that pure substance in the phases alpha, beta or gamma, then I would have said mu alpha would be equal to mu beta would be equal to mu gamma at the triple point. But as you understand, that measurement of chemical potential is not as easy as the measurement of temperature and pressure. And therefore, we wanted to go back and replace the chemical potentials in terms of quantities that we can very easily measure. And that is the reason why we introduced the Clausius equation, or in specific cases, the Clausius-Clapeyron equation. Therefore, if you are thinking of how to change the phase equilibrium temperature for two coexisting phases, then you would revisit the Clapeyron equation or the Clausius-Clapeyron equation, as the case may be, and try and understand that if you increase the pressure, how will the corresponding transition temperature change? Thank you.